Big data is data sets that are so voluminous and complex that traditional data processing application software are inadequate to deal with them. Big data challenges include capturing data, data storage, data analysis, search, sharing, transfer, visualization, querying, updating and information privacy. There are three dimensions to big data known as volume, variety, and velocity. Lately, the term big data tends to refer to the use of predictive analytics, user behavior analytics, or certain other advanced data analytics methods that extract value from data, and seldom to a particular size of data set. There is little doubt that the quantities of data now available are indeed large, but that's not the most relevant characteristic of this new data ecosystem. Analysis of data sets can find new correlations to spot business trends, prevent diseases, combat crime, and so on. Scientists, business executives, practitioners of medicine, advertising, and governments alike regularly meet difficulties with large data sets in areas including internet search, fintech, urban informatics, and business informatics. Scientists encounter limitations in e-science work, including meteorology, genomics, connectomics, complex physics simulations, biology, and environmental research. Data sets grow rapidly, in part because they are increasingly gathered by cheap and numerous information-sensing Internet of Things devices such as mobile devices, aerial, remote sensing, software logs, cameras, microphones, radio frequency identification, RFID, readers and wireless sensor networks. The world's technological per capita capacity to store information has roughly doubled every 40 months since the 1980s. As of 2012, every day 2.5 exabytes, 2.5 times 1018, of data are generated. By 2025, IDC predicts there will be 163 zettabytes of data. One question for large enterprises is determining who should own big data initiatives that affect the entire organization. Relational database management systems and desktop statistics and visualization packages often have difficulty handling big data. The work may require massively parallel software running on tens, hundreds, or even thousands of servers. What counts as big data varies depending on the capabilities of the users and their tools, and expanding capabilities make big data a moving target. For some organizations, facing hundreds of gigabytes of data for the first time may trigger a need to reconsider data management options. For others, it may take tens or hundreds of terabytes before data size becomes a significant consideration. Definition: the term has been in use since the 1990s, with some giving credit to John Mackay for coining or at least making it popular. Big data usually includes data sets with sizes beyond the ability of commonly used software tools to capture, curate, manage, and process data within a tolerable elapsed time. Big data philosophy encompasses unstructured, semi-structured, and structured data, however the main focus is on unstructured data. Big data size is a constantly moving target, as of 2012 ranging from a few dozen terabytes to many petabytes of data. Big data requires a set of techniques and technologies with new forms of integration to reveal insights from data sets that are diverse, complex, and of a massive scale. In a 2001 research report and related lectures, Meta Group, now Gartner, defined data growth challenges and opportunities as being three-dimensional, i.e. increasing volume, amount of data, velocity, speed of data in and out, and variety, range of data types and sources. Gartner, and now much of the industry, continue to use this 3Vs model for describing big data. In 2012, Gartner updated its definition as follows: big data is high volume, high velocity, and/or high variety information assets that demand cost-effective, innovative forms of information processing that enable enhanced insight, decision-making, and process automation. Gartner's definition of the 3 V's is still widely used, and in agreement with a consensual definition that states that big data represents the information assets characterized by such a high volume, velocity, and variety to require specific technology and analytical methods for its transformation into value. Additionally, a new V veracity is added by some organizations to describe it, revisionism challenged by some industry authorities. The 3 V's have been expanded to other complementary characteristics of big data. Volume: big data doesn't sample, it just observes and tracks what happens. Velocity: big data is often available in real time. Variety: big data draws from text, images, audio, video, plus it completes missing pieces through data fusion. Machine learning: big data often doesn't ask why and simply detects patterns. Digital footprint: big data is often a cost-free byproduct of digital interaction. The growing maturity of the concept more starkly delineates the difference between big data and business intelligence. Business intelligence uses descriptive statistics with data with high information density to measure things, detect trends, etc. Big data uses inductive statistics and concepts from nonlinear system identification to infer laws, regressions, nonlinear relationships, and causal effects, from large sets of data with low information density to reveal relationships and dependencies, or to perform predictions of outcomes and behaviors. Characteristics: big data can be described by the following characteristics. Volume: the quantity of generated and stored data. The size of the data determines the value and potential insight and whether it can actually be considered big data or not. Variety: the type and nature of the data. This helps people who analyze it to effectively use the resulting insight. Velocity: in this context, the speed at which the data is generated and processed to meet the demands and challenges that lie in the path of growth and development. Variability: inconsistency of the data set can hamper processes to handle and manage it. Veracity: the data quality of captured data can vary greatly, affecting the accurate analysis. Factory work and cyber-physical systems may have a 6C system. Connection, sensor and networks. Cloud, computing and data on demand. Cyber, model and memory. Content/context, meaning and correlation. Community, sharing and collaboration. Customization, personalization and value. Data must be processed with advanced tools, analytics and algorithms, to reveal meaningful information. For example, to manage a factory one must consider both visible and invisible issues with various components. Information generation algorithms must detect and address invisible issues such as machine degradation, component wear, etc. on the factory floor. Architecture: big data repositories have existed in many forms, often built by corporations with a special need. Commercial vendors historically offered parallel database management systems for big data beginning in the 1990s. For many years, Winter Corp published the largest database report. Teradata Corporation in 1984 marketed the Parallel Processing DBC 1012 system. Teradata systems were the first to store and analyze 1 terabyte of data in 1992. Hard disk drives were 2.5 GB in 1991, so the definition of big data continuously evolves according to Kreider's law. Teradata installed the first petabyte-class RDBMS-based system in 2007. As of 2017, there are a few dozen petabyte-class Teradata relational databases installed, the largest of which exceeds 50 PB. Systems up until 2008 were 100% structured relational data. Since then, Teradata has added unstructured data types including XML, JSON, and Avro. In 2000, Seasoned Incorporated, now LexisNexis Group, developed a C++-based distributed file sharing framework for data storage and query. The system stores and distributes structured, semi-structured, and unstructured data across multiple servers. Users can build queries in a C++ dialect called ECL. ECL uses an apply schema on read method to infer the structure of stored data when it is queried, instead of when it is stored. In 2004, LexisNexis acquired Seasoned Incorporated and in 2008 acquired ChoicePoint, Inc., and their high-speed parallel processing platform. The two platforms were merged into HPCC, or High Performance Computing Cluster, systems, and in 2011, HPCC was open-sourced under the Apache v2.0 license. Quantcast file system was available about the same time. In 2004, Google published a paper on a process called Mapreduce that uses a similar architecture. The Mapreduce concept provides a parallel processing model, and an associated implementation was released to process huge amounts of data. With Mapreduce, queries are split and distributed across parallel nodes and processed in parallel, the map step. The results are then gathered and delivered, the reduce step. The framework was very successful, so others wanted to replicate the algorithm. Therefore, an implementation of the Mapreduce framework was adopted by an Apache open-source project named Hadoop. MIC 2.0 is an open approach to information management that acknowledges the need for revisions due to big data implications identified in an article titled Big Data Solution Offering. The methodology addresses handling big data in terms of useful permutations of data sources, complexity in interrelationships, and difficulty in deleting, or modifying, individual records. 2012 studies showed that a multiple-layer architecture is one option to address the issues that big data presents. A distributed parallel architecture distributes data across multiple servers. These parallel execution environments can dramatically improve data processing speeds. This type of architecture inserts data into a parallel DBMS, which implements the use of Mapreduce and Hadoop frameworks. This type of framework looks to make the processing power transparent to the end user by using a front-end application server. Big data analytics for manufacturing applications is marketed as a 5C architecture: connection, conversion, cyber, cognition, and configuration. The data lake allows an organization to shift its focus from centralized control to a shared model to respond to the changing dynamics of information management. This enables quick segregation of data into the data lake, thereby reducing the overhead time. Technologies. A 2011 McKinsey Global Institute report characterizes the main components and ecosystem of big data as follows. Techniques for analyzing data, such as A/B testing, machine learning and natural language processing. Big data technologies, like business intelligence, cloud computing and databases. Visualization, such as charts, graphs, and other displays of the data. Multidimensional big data can also be represented as tensors, which can be more efficiently handled by tensor-based computation, such as multilinear subspace learning. Additional technologies being applied to big data include massively parallel processing, MPP, databases, search-based applications, data mining, distributed file systems, distributed databases, cloud and HPC-based infrastructure, applications, storage and computing resources, and the Internet. Although many approaches and technologies have been developed, it still remains difficult to carry out machine learning with big data. Some but not all MPP relational databases have the ability to store and manage petabytes of data. Implicit is the ability to load, monitor, backup, and optimize the use of the large data tables in the RDBMS. DARPA's topological data analysis program seeks the fundamental structure of massive data sets, and in 2008 the technology went public with the launch of a company called ISD. The practitioners of big data analytics processes are generally hostile to slower shared storage, preferring direct attached storage, DAS, in its various forms from solid-state drive, SSD, to high-capacity SATA disk buried inside parallel processing nodes. The perception of shared storage architectures, storage area network, SAN, and network-attached storage, NAS, is that they are relatively slow, complex, and expensive. These qualities are not consistent with big data analytics systems that thrive on system performance, commodity infrastructure, and low cost. Real or near real-time information delivery is one of the defining characteristics of big data analytics. Latency is therefore avoided whenever and wherever possible. Data in memory is good, data on spinning disk at the other end of a FC SAN connection is not. The cost of a SAN at the scale needed for analytics applications is very much higher than other storage techniques. There are advantages as well as disadvantages to shared storage in big data analytics, but big data analytics practitioners as of 2011 did not favor it. Applications. Big data has increased the demand of information management specialists so much so that Software AG, Oracle Corporation, IBM, Microsoft, SAP, EMC, HP and Dell have spent more than $15 billion on software firms specializing in data management and analytics. In 2010, this industry was worth more than $100 billion and was growing at almost 10% a year, about twice as fast as the software business as a whole. Developed economies increasingly use data-intensive technologies. There are 4.6 billion mobile phone subscriptions worldwide, and between 1 billion and 2 billion people accessing the Internet. Between 1990 and 2005, more than 1 billion people worldwide entered the middle class, which means more people became more literate, which in turn lead to information growth. The world's effective capacity to exchange information through telecommunication networks was 281 petabytes in 1986, 471 petabytes in 1993, 2.2 exabytes in 2000, 65 exabytes in 2007, and predictions put the amount of Internet traffic at 667 exabytes annually by 2014. According to one estimate, 1/3 of the globally stored information is in the form of alphanumeric text and still image data, which is the format most useful for most big data applications. This also shows the potential of yet unused data, i.e. in the form of video and audio content. While many vendors offer off-the-shelf solutions for big data, experts recommend the development of in-house solutions custom-tailored to solve the company's problem at hand if the company has sufficient technical capabilities. Government. The use and adoption of big data within governmental processes allows efficiencies in terms of cost, productivity, and innovation, but does not come without its flaws. Data analysis often requires multiple parts of government, central and local, to work in collaboration and create new and innovative processes to deliver the desired outcome. International development. Research on the effective usage of information and communication technologies for development, also known as ICT4D, suggests that big data technology can make important contributions but also present unique challenges to international development. Advancements in big data analysis offer cost-effective opportunities to improve decision-making in critical development areas such as healthcare, employment, economic productivity, crime, security, and natural disaster and resource management. Additionally, user-generated data offers new opportunities to give the unheard a voice. However, long-standing challenges for developing regions such as inadequate technological infrastructure and economic and human resource scarcity exacerbate existing concerns with big data such as privacy, imperfect methodology, and interoperability issues. Manufacturing. Based on TCS 2013 Global Trend Study, improvements in supply planning and product quality provide the greatest benefit of big data for manufacturing. Big data provides an infrastructure for transparency in manufacturing industry, which is the ability to unravel uncertainties such as inconsistent component performance and availability. Predictive manufacturing as an applicable approach toward near-zero downtime and transparency requires vast amount of data and advanced prediction tools for a systematic process of data into useful information. A conceptual framework of predictive manufacturing begins with data acquisition, where different type of sensory data is available to acquire, such as acoustics, vibration, pressure, current, voltage and controller data. Vast amount of sensory data in addition to historical data construct the big data in manufacturing. The generated big data acts as the input into predictive tools and preventive strategies such as prognostics and health management, PHM. Healthcare. Big data analytics has helped healthcare improve by providing personalized medicine and prescriptive analytics, clinical risk intervention and predictive analytics, waste and care variability reduction, automated external and internal reporting of patient data, standardized medical terms and patient registries, and fragmented point solutions. Some areas of improvement are more aspirational than actually implemented. The level of data generated within healthcare systems is not trivial. With the added adoption of mHealth, eHealth and wearable technologies, the volume of data will continue to increase. This includes electronic health record data, imaging data, patient-generated data, sensor data, and other forms of difficult-to-process data. There is now an even greater need for such environments to pay greater attention to data and information quality. Big data very often means dirty data, and the fraction of data inaccuracies increases with data volume growth. Human inspection at the big data scale is impossible, and there is a desperate need in health service for intelligent tools for accuracy and believability control and handling of information missed. While extensive information in healthcare is now electronic, it fits under the big data umbrella as most is unstructured and difficult to use. Education. A McKinsey Global Institute study found a shortage of 1.5 million highly trained data professionals and managers in a number of universities, including University of Tennessee and UC Berkeley, have created master's programs to meet this demand. Private boot camps have also developed programs to meet that demand, including free programs like the Data Incubator or paid programs like General Assembly. Media. To understand how the media utilizes big data, it is first necessary to provide some context into the mechanism used for media process. It has been suggested by Nick Kudry and Joseph Turo that practitioners in media and advertising approach big data as many actionable points of information about millions of individuals. The industry appears to be moving away from the traditional approach of using specific media environments such as newspapers, magazines, or television shows, and instead taps into consumers with technologies that reach targeted people at optimal times and optimal locations. The ultimate aim is to serve or convey a message or content that is, statistically speaking, in line with the consumer's mindset. For example, publishing environments are increasingly tailoring messages, advertisements, and content, articles, to appeal to consumers that have been exclusively gleaned through various data mining activities. Targeting of consumers, for advertising by marketers. Data capture. Data journalism. Publishers and journalists use big data tools to provide unique and innovative insights and infographics. Channel 4, the British public service television broadcaster, is a leader in the field of big data and data analysis. Internet of Things, IoT. Big data and the IoT work in conjunction. Data extracted from IoT devices provides a mapping of device interconnectivity. Such mappings have been used by the media industry, companies, and governments to more accurately target their audience and increase media efficiency. IoT is also increasingly adopted as a means of gathering sensory data, and this sensory data has been used in medical and manufacturing contexts. Kevin Ashton, digital innovation expert who is credited with coining the term, defines the Internet of Things in this quote: "If we had computers that knew everything there was to know about things using data they gathered without any help from us, we would be able to track and count everything, and greatly reduce waste, loss, and cost. We would know when things needed replacing, repairing, or recalling, and whether they were fresh or past their best." Information technology. Especially since 2015, big data has come to prominence within business operations as a tool to help employees work more efficiently and streamline the collection and distribution of information technology, IT. The use of big data to resolve IT and data collection issues within an enterprise is called IT Operations Analytics, ITOA. By applying big data principles into the concepts of machine intelligence and deep computing, IT departments can predict potential issues and move to provide solutions before the problems even happen. In this time, ITOA businesses were also beginning to play a major role in systems management by offering platforms that brought individual data silos together and generated insights from the whole of the system rather than from isolated pockets of data. Case studies. Government. United States of America. In 2012, the Obama administration announced the Big Data Research and Development Initiative, to explore how big data could be used to address important problems faced by the government. The initiative is composed of 84 different big data programs spread across 6 departments. Big data analysis played a large role in Barack Obama's successful 2012 re-election campaign. The United States federal government owns 6 of the 10 most powerful supercomputers in the world. The Utah Data Center has been constructed by the United States National Security Agency. When finished, the facility will be able to handle a large amount of information collected by the NSA over the Internet. The exact amount of storage space is unknown, but more recent sources claim it will be on the order of a few exabytes. India. Big data analysis was tried out for the BJP to win the Indian general election 2014. The Indian government utilizes numerous techniques to ascertain how the Indian electorate is responding to government action, as well as ideas for policy augmentation. United Kingdom. Examples of uses of big data in public services. Data on prescription drugs. By connecting origin, location, and the time of each prescription, a research unit was able to exemplify the considerable delay between the release of any given drug, and a UK-wide adaptation of the National Institute for Health and Care Excellence guidelines. This suggests that new or most up-to-date drugs take some time to filter through to the general patient. Joining up data, a local authority blended data about services, such as road gridding rotas, with services for people at risk, such as Meals on Wheels. The connection of data allowed the local authority to avoid any weather-related delay. Retail. Walmart handles more than 1 million customer transactions every hour, which are imported into databases estimated to contain more than 2.5 petabytes, 2,560 terabytes, of data, the equivalent of 167 times the information contained in all the books in the U.S. Library of Congress. Windermere Real Estate uses location information from nearly 100 million drivers to help new home buyers determine their typical drive times to and from work throughout various times of the day. FICO card detection system protects accounts worldwide. Science. The Large Hadron Collider experiments represent about 150 million sensors delivering data 40 million times per second. There are nearly 600 million collisions per second. After filtering and refraining from recording more than 99.99995% of these streams, there are 100 collisions of interest per second. As a result, only working with less than 0.001% of the sensor stream data, the data flow from all 4 LHC experiments represents 25 petabytes annual rate before replication, as of 2012. This becomes nearly 200 petabytes after replication. If all sensor data were recorded in LHC, the data flow would be extremely hard to work with. The data flow would exceed 150 million petabytes annual rate, or nearly 500 exabytes per day, before replication. To put the number in perspective, this is equivalent to 500 quintillion, 5 times 1020, bytes per day, almost 200 times more than all the other sources combined in the world. The Square Kilometre Array is a radio telescope built of thousands of antennas. It is expected to be operational by 2024. Collectively, these antennas are expected to gather 14 exabytes and store 1 petabyte per day. It is considered one of the most ambitious scientific projects ever undertaken. When the Sloan Digital Sky Survey, SDSS, began to collect astronomical data in 2000, it amassed more in its first few weeks than all data collected in the history of astronomy previously. Continuing at a rate of about 200 GB per night, SDSS has amassed more than 140 terabytes of information. When the Large Synoptic Survey Telescope, successor to SDSS, comes online in 2020, its designers expected to acquire that amount of data every 5 days. Decoding the human genome originally took 10 years to process, now it can be achieved in less than a day. The DNA sequencers have divided the sequencing cost by 10,000 in the last 10 years, which is 100 times cheaper than the reduction in cost predicted by Moore's law. The NASA Center for Climate Simulation, NCCS, stores 32 petabytes of climate observations and simulations on the Discover supercomputing cluster. Google's DNA Stack compiles and organizes DNA samples of genetic data from around the world to identify diseases and other medical defects. These fast and exact calculations eliminate any friction points, or human errors that could be made by one of the numerous science and biology experts working with the DNA. DNA Stack, a part of Google Genomics, allows scientists to use the vast sample of resources from Google's search server to scale social experiments that would usually take years, instantly. 23andMe's DNA database contains genetic information of over 1 million people worldwide. The company explores selling the anonymous aggregated genetic data to other researchers and pharmaceutical companies for research purposes if patients give their consent. Ahmed Hariri, professor of psychology and neuroscience at Duke University who has been using 23andMe in his research since 2009, states that the most important aspect of the company's new service is that it makes genetic research accessible and relatively cheap for scientists. A study that identified 15 genome sites linked to depression in 23andMe's database led to a surge in demands to access the repository, with 23andMe fielding nearly 20 requests to access the depression data in the 2 weeks after publication of the paper. Computational fluid dynamics, CFD, and hydrodynamic turbulence research generate massive data sets. The Johns Hopkins Turbulence Databases, JHTDB, contains over 350 terabytes of spatiotemporal fields from direct numerical simulations of various turbulent flows. Such data have been difficult to share using traditional methods such as downloading flat simulation output files. The data within JHTDB can be accessed using virtual sensors with various access modes ranging from direct web browser queries, access through MATLAB, Python, Fortran, and C programs executing on clients' platforms, to cutout services to download raw data. The data have been used in over 150 scientific publications. Sports. Big data can be used to improve training and understanding competitors, using sports sensors. It is also possible to predict winners in a match using big data analytics. Future performance of players could be predicted as well. Thus, players' value and salary is determined by data collected throughout the season. The movie Moneyball demonstrates how big data could be used to scout players and also identify undervalued players. In Formula One races, race cars with hundreds of sensors generate terabytes of data. These sensors collect data points from tire pressure to fuel burn efficiency. Based on the data, engineers and data analysts decide whether adjustments should be made in order to win a race. Besides, using big data, race teams try to predict the time they will finish the race beforehand, based on simulations using data collected over the season. Technology. eBay.com uses two data warehouses at 7.5 petabytes and 40 PB as well as a 40 PB Hadoop cluster for search, consumer recommendations, and merchandising. Amazon.com handles millions of back-end operations every day, as well as queries from more than 500,000 third-party sellers. The core technology that keeps Amazon running is Linux-based, and as of 2005 they had the world's three largest Linux databases, with capacities of 7.8 TB, 18.5 TB, and 24.7 TB. Facebook handles 50 billion photos from its user base. Google was handling roughly 100 billion searches per month as of August 2012. Oracle NoSQL database has been tested to pass the 1 MOPS/SEC mark with 8 shards and proceeded to hit 1.2 MOPS/SEC with 10 shards. Research activities. Encrypted search and cluster formation in big data were demonstrated in March 2014 at the American Society of Engineering Education.
Please subscribe and thanks for watching.